Next distribution is the geometric. Now let's describe what it is. I've got some results up here. And again, this is fairly easy to understand where it comes from. E of x and var of x will come back at the end if we've got time and try and prove them. They're not desperately tricky though. Now what's the geometric do is basically is this. You try until you succeed. All right, that is the key behind geometric. So it is closely related to the binomial, but you only have one success in the geometric. All right, so the binomial, you're going to do it like 10 times. You're going to count how many times it succeeds. So you do something, it either succeeds or it doesn't. You're going to do it 10 times regardless, and you're going to count how many successes you get. Geometric is you don't know how many times you're going to try, so it's not a fixed n. All right. But it does have a fixed p. So it is related to the binomial in that sense, but we don't have a fixed n, and there's only ever one succeed, and it's the last one. All right, so we've always got that same order, which is why we do not have that binomial coefficient. All right, we don't have to count, oh, the success could come in the first go, the third go, whatever. No, it's always the last go. Okay, so, and this is where the formula comes from, right? If you want to, and we measure the number of attempts. So in fact, the random thing that we are looking at is the number of attempts until you get that first success. All right, and that's the real thing. So whereas the binomial counts how many successes, the geometric counts how many times you have to try until you get one success. And this is, you can see that from our formula, right? If you want x tries, you need to get fail, 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 success. If you want x attempts, you need x minus 1 fails, and you need 1 success. So if the probability of success is p, the probability of failure is 1 minus p. So we want 1 minus p to the x minus 1 times p. Like I said, it's a fairly intuitive distribution, this one. Why is it called geometric? Because you end up with geometric series, basically. So Emma and Leo are playing a game. Good old Emma and Leo. They take turns rolling a fair six-sided dice. Emma goes first. Leo is a gentleman. If either player rolls a 6, they win the game immediately. If not, the other player plays. Find the probability that Emma rolls the first 6 on her second turn. So what needs to happen here? I quite like listing out. So we're going to go, the play pattern is Emma, Leo, Emma, Leo, Emma, Leo, Emma, Leo, etc. Right? So if she is going to roll the first 6 on her second turn, what needs to happen? Well, we need a fail, a success. I.e., if we are looking here at a geometric distribution, the probability of success, i.e. rolling a 6, is 1 in 6. We want the probability, so her second turn is the third term overall. But again, you don't actually need a lot of that. Like, it's fairly intuitive. So you need 2 fails and then a success. So I don't know what that is. That's 25 over 216, isn't it? Whatever that is. Quick math. Probability that the first 6 is rolled on or after Leo's third turn. Right, so let's jot this out as well. So we want our first success to happen on or after Leo's third turn, i.e. we want the probability that x is greater than or equal to, hang on, 1, 2, 3, 4, 5, 6 is greater than or equal to 6. All right, because X is just the number of turns played. X doesn't care whether it's Emma or Leo. Now, there is an easy formula for this, but let me just see, does this thing have geometric? Because I never actually use it for the geometric, but I'm just curious whether or not it does. So we got binomial, we got normal, we got Poisson. We do got geometric, so we can do that. So bigger than or equal to 6, 1 in 6. Let's see. So they reckon it's 0.4018. Now here is a nice formula though, and we're going to jot it up here. Now, what do I need for the first success to happen on the 6th or greater turn? Well, all I really need is I need 5 failures, i.e., I need 5 failures. And what's the probability of getting 5 failures? That is 5 over 6 to the power of 5. And I'm very much hoping that if I do understand how the calculator does this, if I go 5 over 6, nope, to the power of 5, 0.4018, woo! Yes, get in there. So in fact, the calculator's done some rounding when it gave me 4018. I think we could probably go in here as well, right? Distribution, I'm going to assume geometrics in there. GCD, lower 6, upper. Is that 1/6 for me? No. 0.40189. Yeah, you need to be given P, right? Or you have to figure out P. Like in this question here, you can easily figure out P. But here is our formula if you ever want it. So if you want X or more for your success, well, all you need is you need X minus 1 fails. If you go option and F1, you can see the whole number. In what bit? In what bit? Brandon, I'm interested. In which particular bit? Because I've got an... Oh, in the distribution. Is that so? Geometric, Bosch, go option. Oh, go to the cell with the answer. Gotcha. Option F1. Oh, fair enough. Fair enough. There you go. We're learning stuff all the time. We're learning stuff all the time. Brilliant. That's weird that it's rounded it weird though, right? That's weird. Yeah. There you go. Like I say, you can do some really cool stuff with this calculator. It does require like learning, and some of it, like me, I've been using it for years and years and years. The distribution mode is fairly new, I will admit to that, so I'm not completely au fait with it. Right, find the mean and standard deviation of the number of rolls until a 6 is first used. So we can use our results here. E of X is 1 over a 6th, which is 6. And again, actually, when you think about it, something's got a probability of 1 in 6 of happening. You're going to do it until it works. Well, it kind of makes sense. You're going to take 6 goes to get a success, right? Sort of fairly intuitive, right? You've got a probability of 1 in 2. It's going to take 2 goes to do it. 1 in 3, 3 goes, and so on and so forth. So actually, it's a fairly intuitive result. var of X is maybe a little less intuitive. So it's 1 minus P over P squared. Do you know what? I'm feeling funky. So a variance of 30. So standard deviation is square root of 30. I don't know, 5-ish. And yes, path. Now, part 4 is where we don't really have a formula for something like part 4. But we don't really have a formula for it. But if we understand what this distribution is doing, then it's quite useful. So what needs to happen for Emma to win the game? So either she wins on the first go, or she wins on her second go, which requires fail, fail, success. And then she succeeds. Or they each have to fail 2 goes, and then she wins. Or they each fail 3 goes, and then she wins. Okay? So if we start listing out, and I'm a big fan of this in maths in general, as much as we have all these cool, big overall ideas, but sometimes you just want to list out what your options are and what's happening, and you can see the pattern and you can work with it. So what do we have? This is an infinite geometric sequence, which is really why this is called a geometric distribution. We've got first term is 1/6. R is 5 over 6 squared, which is 25 over 36. So this sum is A over 1 minus R. Which is what? Which is 1/6 over 11 over 36, which comes out 6 over 11. Now, intuitively, it's quite interesting, right? 6 over 11, about 50-50. About 50-50. 6 out of 12 would be 50-50. And in this game, right, they each roll a dice. Whoever gets it first wins. It seems like it should be fairly even. However, 6 over 11 is slightly above 50%. Where does that slightly above 50% come from? Well, it's because she goes first. So she gets that one extra little bite at the cherry that Widgie doesn't get. So sum to infinity is in just normal pure. Sum of a geometric is just in normal pure, right? Well, do be careful here, me to say we are not just summing p1 minus p to the n, because this is actually 1 minus p to the 2n, right? Because for her to get the next go, she needs to skip 1. What you'll find is if you actually do the infinite sum of p times 1 minus p to the n, you will just get 1, right? Because all you're doing is you're adding up all the probabilities, so you should just get 1. If you're interested, put that on the list of things we can try and prove. Timing wise, we might have a few minutes at the end. Yeah. So that's just a really cool question. I quite like it, but it's understanding what the geometric distribution does. I reckon we got one more slide in us, and then we'll take a 5-minute breather. I mean, yes, n will change based on the gap size, but really I've taken one example of where someone can play around with the geometric a little bit. Really, you do need to just, this is where I've spent some time trying to explain what the geometric does, because if you understand what it models, then you are much better off. Okay, there are a few results that are good to have, and you do get given a lot of them in the formula booklet. But the real tool here is going to be your brain. The real thing is going to be you thinking of this in a case-by-case scenario. What is going on physically in this scenario, and what maths tools do I have at my disposal? That is what you want here. Okay.